Okay, linear functions preserve linear combinations, linear operators. That's the way I chose to call it. Linear operator is a function to begin with, but it preserves linear combinations. We'll see why it is important in shortly, but examples that follow really give you just right away a bunch of examples of linear functions that are certainly are important. And those are, as I said, stretches, rotations, and so on. One of them can be very explicitly written as is, and others maybe not so much, not yet. Okay, so as you can see, once again, rotation, as you can see, summation is nothing is going to happen to summation. If you rotate a piece of paper, it's the same. The sum remains the sum. Okay, so if x and y have been rotated, then x plus y has been rotated the same angle, and it's the same because of the congruency of the triangles, it will produce the same result. Scale multiplication is even simpler. Okay, stretching is not as simple, but uniform stretching is. And indeed, the triangle become similar. They're not identical, but they're similar triangles to the original. So this is what I'm talking about. And once again, if you have a parallelogram, you stretch it uniformly, then its diagonal remain the diagonal. So summation is preserved once again. Okay. So these are the examples of linear operations. So there are more. One, you remember. Something that's not on the list, it is non-uniform stretching. Okay, horizontal not the same as vertical. And then there are multiple combinations of these operations, especially in higher dimensions. Think about if you talk about three-dimensional space and just consider motions, three-dimensional motions. So it could be not only stretching, but let's say motion. A motion could be just rotation around this axis and then around that axis, and then more. Okay, so what is it? It does seem to be already clear. It seems clear that they all will be linear, right? So if you're rotating a piece of paper with addition on it, and it is the same. Addition is preserved. Imagine that our three-dimensional space is also rotated, maybe in some direction. So once again, if you had two vectors added together, you have pretty much the same picture. You have a parallelogram, you rotate the parallelogram, and the diagonal of that parallelogram remains also a parallelogram in the new place. So then it's also a linear operator. Okay, so it's all good, and the point I want to make repeatedly, and that is this all applies. Equally applies to all subspaces or spaces with or regardless of any basis. Okay, remember every subspace can have multiple bases. All that have been described up to now, definition of a linear operator, examples of rotations to confirm that it is indeed linear stretching, rotation, reflections can all be described without referring to the basis. Okay, so just to illustrate that, so in R2 we have this is a basis, and that is a basis, and this is a basis, and this is a basis. All of these are bases. And this is not a basis. Okay, so two vectors in R2, as long as they are linearly independent, in other words, they're not multiples of each other, they form a basis, and it doesn't matter what the basis is. The basis is needed for recordings, to keep track for bookkeeping, and to make things explicit. But if we think of linear operators as transformations, then it doesn't matter. If we can describe them independent of the basis, then we do. And one example is very simple when it works out in any dimension is f of x is equal to, say, ax. What is it? Is a stretch. It's a stretch. So a is fixed. A is the real number fixed, and you just take every vector multiplied by a number. And you have your stretch. clearly it is linear. It is linear. Just proof. Proof that it is linear. So f of say x plus y is equal to ax plus y. And what we know about the algebra of vectors, this is equal to ax plus ay, right? The distributive property of addition and scalar multiplication, and this is equal to f of x plus f of y. Okay, so that shows that indeed this is a linear. At least it preserves addition. Okay, so there you go. You have a linear function in any dimension of any space. So this one is from Rn to Rn, any dimensional space or subspace, and then we can prove that it's a linear operator without referring to bases. But we have to refer to the bases inevitably, because if we want to analyze it, say anything specific about them, we gotta go with the bases. Okay, so here's another example, and almost similar to this. F of x is equal to fx, where f is what? F is any matrix. Okay, so the variety certainly goes up enormously. The only problem is that we cannot speak of this without the basis. There is no matrix unless the basis has been specified. So we need a basis. So from now on, we're talking about a space equipped with not equipped, but rather with a basis specified. It could be the standard basis or maybe not. It doesn't matter. As you can see, not only the vectors don't have to be unit vectors, they don't have to be perpendicular to each other. As long as they're not, as long as they're linearly dependent, we have a basis. Okay, so this is how we proceed. We suppose that, say x, let's say V, is a vector, is a subspace. A subspace, or specifically could be Rn, with a basis specified. Specified meaning that why do we have to specify a basis? We could just for the point of saying that it is not necessarily the standard basis. But we start with the standard basis. Okay, so that's the general setting. But I think let's start small, and let's just take the two-dimensional space and with the standard basis. Okay, so in other words, E1 is equal to 1, 0, E2 is equal to 0, 1. That's my basis. The only difference is that I will keep referring to this as a basis rather than just a formula. Okay, so F is just a matrix. So 2 by 2 matrix. So as we have used, the language we have used was A11, A12, A21, A22. So in other words, nothing but 4 numbers. That's what the matrix is. They are arbitrarily picked from the real numbers, put in this table, and then what? So this is given just a matrix, a 2 by 2 matrix, and then define a function. I will use the same name from R2 to R2. In other words, now a vector is an input and vector is the output. So how? It's simple. F of x is equal to fx. So you see the difference between what we have on the left and what we have on the right. So this is a function notation, meaning that f stands for the name of the function is f capital, and then in parentheses you have the input, x, which happens to be a vector on the plane. On the right, this is matrix multiplication. Okay, so far it's just a function. If we want to define this through matrix multiplication, now if I want to be specific here, I will write it as matrix multiplication. So it will be A11, A12, A22, A21, A22, matrix multiplied by XY. You know, let's make our life easier. How about I put rather than dealing with indices, we'll have to deal with indices sooner or later, but let's say A, B, C, D. Just keep it simple. So A, B, C, D multiplied by XY. We carry out this multiplication. What do we have? AX plus B plus BY, CX plus DY. Okay, that's my output vector. And so as you can see, if so what is the meaning of this? X is equal to xy, the input vector, and the output vector is, say, u, once again with two components, u and v, and both of them belong to R2, but these are, you better think of these as two different copies of R2, even though in both cases the basis is the same, chosen to be the standard Euclidean basis. Okay, so then you can break it apart if necessary, sort of kind of a backtracking to something more elementary, but it's worthwhile to just to see what is that matrix notation, matrix multiplication gives us, and it's really uncomplicated. Then I have, if I take this as UV, this is UV, right? So I carried out my computation of the of my matrix multiplication. I'm supposed to end up with UV, and then U and V, those lowercase u and v, can be now expressed in terms of x and y lowercase. So I have U equal to AX plus BY, and V is equal to CX plus DY. Okay, so if you look at these two functions separately, AX plus BY, what is it? AX plus BY. How would you? Well, it should be something familiar. Well, or not, depending on whether or not you took Calc 3. It's a function of two variables, a real valued function of two variables. X is one variable, y is the other variable, and in fact, you can think of also that was discussed in this class. It's a plane, right? So x and y are the variables, is the xy plane, and then u is the third variable. So you would illustrate, how would I illustrate this thing over here? I would illustrate it with two graphs. These are functions of two variables, and I could illustrate them with two graphs. In fact, these are functions of two variables. Both of them are linear functions. So this is one, x, y, u, and there is a plane in it, and then the second one is x, y, v. And we have two planes, and these are not just any plane, but these planes are, what's so special about these two planes? No, they pass through the origin. So there is no that extra term. Okay, so as you can see, I made sure that both of them pass through the origin to begin with, and then why it is just a triangle, because these two lines on the left and the right is where this plane crosses the xu, yu planes. Okay, so as if we are only can see what's happening in this octet. You remember that term? The three-dimensional space is divided into 8 I'm sorry, 6 pieces, six segments. The plane is cut into 4, that's why we call them quadrants. The space is cut into 6, we call them octants. And so this is just one octant, which is directly between the 3 coordinate axes. Okay, except that's the difficulty that we're facing in comparison that what we have seen so far in those 2 functions. We have 2. We have 2 functions of 2 variables. Taken together, they give us function that is a vector variable and a vector valued. Okay, so this is the function that I'm talking about. It is simultaneously vector valued. Okay, so f is vector valued. I'm sorry, vector variable. That variable being x, and it is also vector valued. That is u. Okay. So we combine those variables into vectors, as we have been doing that for a while. But in this case, you have both input and outputs are both vectors. Okay. If you want to cut it back, you end up with 2. So 1 and the other one. As you can see, it's hard to visualize. Hard to visualize is a very, very simple function, but if you try to plot the graph of these 2 functions, you will end up for 2 3-dimensional pictures that are not really related to each other in any way. So that's why it is preferable, I believe, to think about a function like that as a transformation of the plane. So it's rotation, stretch, and so on. Okay, so so we have demonstrated already. We're not demonstrated yet, but so this was just an example of what is an example of how a matrix, given matrix, gives you a function. Do you see that this is a linear function? Not just any function, but the linear function. F is a linear operator, as it has been defined. It has been defined as such a function that preserves linear combinations. Where does that conclusion come from? It comes from the what we know about matrix multiplication. So for example, if I have f of x plus y, right, it is equal to fx plus y. Matrix, this is matrix multiplication again. I'm multiplying vector matrix f by the sum of 2 vectors x and y. And then, remember that discussion there is a distributive property of matrix multiplication. So it is equal to fx plus fy. Okay, and then you write it out fx plus fy. So that is why the summation is preserved. Scalar multiplication is even simpler. So f(ax), a can be, so we're using the associative, associative or constant multiple property of matrix multiplication, and then we end up with, once again, the scalar multiple to be scalar multiplication to be preserved under matrix multiplication. So I mean, let's demonstrate, just because we're doing 2-dimensional stuff. Let's demonstrate this quickly, why this works out. Maybe so that we don't have to go so far back trying to think about it. So I have a, b, c, d multiplied by x, y plus, say, x prime, y prime. Right? So this is the summation, and it's supposed to come out on the other end with well, we'll see what we're coming up with. So let's just multiply. Well, we add and then we'll multiply. So I'll have a, b, c, d, my matrix, and I have a vector, which is, what's the vector? No, I want to carry out the addition. x plus x prime and y plus y prime, right? Okay. Now I carry out matrix multiplication. So what do I get? What's the first entry? Ax plus x prime plus by plus y prime, right? So columns, rows are multiplied by columns. We have only one column, right? So that's what we get, and then we have the same, but for the second entry, we have c x plus x prime, and we have dy plus y prime. Okay. So I'm going to just simplify to demonstrate that indeed we're going to end up where we want to end up. So what I'm going to do, I'm going to just distribute distribute pretty much. So what I'm getting here is ax plus by plus ax prime plus by prime, right? So I'm just expanding combining x's, y's together separate from x prime, y prime. So I'll have cx plus dy, and I have cx prime plus dy prime. Okay? Okay, that seems to make sense. Now, you see what I'm doing next? What? Split it down the middle. Ax plus by, cx plus dy, plus the other one, ax prime plus by prime, cx prime plus dy prime. Okay, and the last step is, what's the last step? What? No, we just split it. We don't want to go back. What is the first vector? No. No. A, B, C, D what? Right. So it is in fact the product of the same matrix that we have had, A, B, C, D, multiplied by the vector x, y. Right? Well, that's what we're after anyway. Right? And here we have the same vector A, B, C, D multiplied by x prime, y prime. Okay, so that is, you can call it sum rule, you can call it linearity, you can call it the distributive property of matrix multiplication. Doesn't really matter. Right now we prefer the first one, so it is linearity of matrix multiplication. So as you can see, addition turns this one. Addition turns into addition. So that's what we mean when we say addition is preserved. Addition, and then when you carry all the operations, then you still have addition. So you can compute this thing in two ways. Either you first add on the left, and then you multiply by the matrix, or you first do multiplication by the matrix by each of those two participants, and then add them together. Okay, and the result is the same. So that's the linearity. Scalar, so that we took care of this. The second one is a bit even simpler. Scalar multiplication does not require as much work, but we have this summation demonstrated. So indeed it is a linear operator. That is the conclusion that we have drawn, that matrix produces a linear operation, linear operator. Now the next, let me put it in a bigger way. So suppose x V is once again Euclidean space, or space with a basis specified. Then every matrix produces matrix F produces a linear operator the way I have specified. So f of x is equal to fx. Okay? So, so every matrix is in fact a linear operator as long as the produces a linear operator by this formula. So you remember you can describe a function implicitly in some like a transformation words using word stretching and so on, or you can specify. You can go specifically and say, let's suppose our function looks like this. It is a multiplication by a matrix. So so every matrix F produces a matrix. Well, let's be specific. That's probably important. So if this is an n-dimensional space, then well, let's stick with this for now. Suppose we have a Euclidean space Rn, and with the basis specified, we pick any matrix n by n, arbitrary. We multiply x by that matrix. Altogether, that will give us a linear operator. Okay, so that's a good. There is a. Can we reverse this statement? Every n by n matrix produces a linear operator. The important part is also the vice versa part. How would you put it?
Every linear operator produces an n by n matrix.
Or is given by a matrix, yes. Every linear operator, say f from Rn to Rn, is produced by some matrix, n by n, naturally. Okay, so that's quite a profound discovery. So matrices, linear operators are matrices, as long as the basis is specified. Okay, so if basis is specified, then every linear operator can be turned into a matrix. And then if you already have a matrix, then you just that is definitely a linear operator. Okay, so that's the good news. It means that we have a linear operator, then we can find a matrix for it. It just takes some work. It can be made more specific, and that's what I want to try to do. So let's make the second part specific. So suppose we have a linear operator, f, from, once again, R2 to R2, with a specified basis. Okay? So let's find a matrix for it. Specific linear operator. Find its matrix. Okay. So how would we do it? Well, the function is given, so for every input we know its output. That's what function is. How we don't know. It might be more specific than that.
Nodes 2 by 2.
Yeah. So f is A, B, C, D. Find A, B, C, D. Find A, B, C, D such that, once again, f of x is equal to f of x. Okay, so this is known. The function is known, and these need to be found. So based on our information about how inputs produce outputs, we need to find this particular way how it is done. How can we? Well, let's maybe not try to guess how it's done. Let's do a couple of specific problems. Specific operators. For example, f is once again I describe it verbally. is a stretch. Is a stretch by 2. Okay, so let's find a matrix for it. Okay, so f of x, as we know, is equal to 2x. That's what stretch is. Okay, so how do we find a matrix? How do we express this as a matrix multiplication? A, B, C, D, x, y is equal to 2xy Okay, so we need to find A, B, C, D. So what do? I would actually have to carry out this operation. I already have, okay, so first of all, this is 2x to y, but we have carried out that operation already once, right? Where is it? Here it is. So we don't have to do it again, right? So A, B, C, D by xy is equal to x plus by, cx plus dy. Okay, so we can use that. Okay, so so on the right I'm supposed to have 2x to y. On the left, as I would just multiply, I'll have ax plus by once again. And here I have cx plus dy. So we compare the left-hand side to the right-hand side, and we produce, not surprisingly, we produce a system of linear equations. Ax plus by is equal to 2x, and cx plus dy is equal to 2y. Okay, so and then we need to find A, B, C, and D. Can you guess? A is 2, what else? We need 4 numbers. B is 0. C is 0, and D is 2, right? So our matrix is 2, 0, 0, 2. Okay, so all right, so that's a good lesson. In fact, let's try, since we are at it, what about Rn? So we have f is still stretched by 2, so that formula at the top still applies. Can you suggest the matrix, n by n matrix?
2 times the identity matrix?
Well, yeah, that's pretty much two times the identity matrix, right? So this is twice the identity matrix, right? So I'm sorry, there is no D there. We don't use D. Okay. So then it's easy. Fx is, if it is 2ix, what is it? It's simply equal to, I is gone, and I have 2x. Okay. I guess it's still worthwhile to see what the matrix looks like. Twice the identity matrix, 2i. What does it look like? The identity matrix has ones on the diagonal, and the rest are zeros. When you multiply by 2, you multiply everything by 2. Just be made of 2's. And we have zeros here. Okay? So this was a little bit more than necessary in order to, so we had to solve it. What if we have, well, let's do, okay, so let's step away slightly and go backwards. What is this? If my matrix is 2, 0, 0, 3, what does it do? It stretches more horizontally than vertically, which actually, if you look at it, what the result it produces is not exactly that's what it does to a circle. That's what it does to a circle. So if you have a circle, it will turn into an ellipse, non-circular ellipse. So it will be stretched more horizontally than vertically, indeed. So a circle, I think I showed you that before, so it will be stretched, maybe not like this, it will be still bigger, but stretched more horizontally than vertically, like this. Okay, so you can see when and now if you go to n-dimensional space, you can imagine, and you still have a matrix that is called diagonal matrix. In other words, a matrix that has zeros everywhere except for the main diagonal. Then think about it. So let me do the diagonal matrix. F is equal to, say, D1, D2, D3, Dn, and these are all zeros. Okay? So if I start multiplying it by x, fx will be this matrix multiplied by x1, xn, right? So if I start multiplying row by column, what I'm going to get? Each row is multiplied by the column, the same column. Each row will have all zeros except for one entry. Right, so yeah, so it will be dx1, dx2, I'm sorry, d1x1, d2x2, dn xn. So you can certainly interpret it as stretch in the direction, different degree of stretching in different directions along each of the axes. Then it is not hardly obvious how do you stretch it in the direction other than the axes. How do you stretch like this? Okay, so, well, let's not worry about that just yet. Let me do something else. And now, suppose F is the flip about the x-axis. So, in other words, this point becomes that point. That's what the flip is. You don't have to go all the way back, and you just can ask yourself what are the formulas. So where does xy go? Where does xy go? Say it again. X negative 1.
Oh.
Right? That's all. Yeah, so that's what the flip is. Right? So x is the same, and so it's a piece of paper flipped. Right? So it actually is sufficient to look at this, what I've got here, and to write the the matrix. So f of xy is x negative y. So all you have to do is to think of a matrix X that would produce this result. So as you can see, nothing happens to X. We already know what it means. Negative 1 on the diagonal, the rest is zeros. Okay, so there you go. Okay, it's a flip. If you want to flip about the y-axis, then you do what? So about the y-axis, what's the matrix? Negative 1, 0, 0, 1. Okay, what about the diagonal? No. Well, this is certainly a good question next to be asked. If what is negative 1, negative 1? We'll ask that question next. What about the diagonal? Once again, draw a picture if in any doubt. This is my diagonal. So this point goes over here. That's a flip. So point xy, where does it go? Remember calculus 1, when you do this flip? You do inverses. What's the meaning of the inverse? Xy becomes yx, right? So the matrix is then yeah, 0, 0, 1, 1, 0, right? Okay, so that's going to flip it. So it's not this is not diagonal, by the way, anymore. Diagonal, there's only one main diagonal. It goes 45 degrees. This isn't the diagonal. This is the other diagonal. Okay, so what is then what is this? What is this?
Reflection at the origin.
Yeah, it is. So also known as the central symmetry. So going like this, from this point to that point. So xy goes to negative x, negative y. So as you can see, you can do either points. Sometimes points are easier to analyze. It's just more than vectors. We are talking about vectors. Definitely, it is vector multiplication, matrices, and all this is all linear algebra. But sometimes you can just go back to things that you know from calculus and and see what happens to those points x, y when you either do inverse, you do some kind of symmetry, you do. We're not going to do shifts, but other than the reflection, one, the other one, that's how it works out. We talked about that already, so let's do it one more time, and that is 90 degrees rotation. So once again, xy becomes what? So just need to first figure out what it means to rotate it. So if I have xy here, and I rotate it like this, what is the new coordinates? 90 degrees. No. What?
That was negative x bar.
No. Almost. You still you flip the variables again,
Oh.
right?
Oh yeah.
So it will be negative. So the x coordinate becomes negative y, right? So negative yx, right?
Oh, because you're only the other axis, you're not doing
Yeah,
axes, okay.
yeah. And the matrix is then, once again, you already have a bit of experience to tell what the matrix should be. It is similar to that flip that we had 45 degrees, about the diagonal flip, except it had over here, see, this one, 1 and 1, and it's, instead of 1 and 1, we're going to have what? Negative 1 and 1. Like this. Okay? I don't want to go through the whole derivation of the general case. Rotation through angle alpha. It's a matrix. As you'd expect, you'll have trig functions. Okay? So I don't think there is, well, let me just write it out. Nope. Don't want to mess it up. Sine alpha, cosine alpha, minus cosine alpha. I hope I did not mess it up. Okay, so if alpha is equal to pi over 2, sine of pi, yeah, I didn't mess it up, did I? So 45 degrees rotation, sine of 45 degrees, sine of pi over 2 is 1. So okay, so I messed up sine and cosine the opposite way. Yeah, sorry about that. So cosine on the diagonal cosines, on the other diagonal sines with one negative. Okay, so once again, if alpha is pi over 2, cosine of alpha then is equal to 0, and sine of alpha is equal to 1. And that's how you get this matrix over here. That particular case. So rotation, as I said, through pi over 2. What happens if alpha is pi?
Isn't that a 180 degree rotation?
It is what?
A 180 degree?
Yes. Yes. So let's find the matrix. So this is the general R sub alpha. How about I call this matrix R sub alpha? So alpha is pi. Cosine of alpha then becomes what?
I got a question.
Yeah.
So how did you get your signs on that one? Like, am I missing something here? Like, if
You
you're,
put the negative in the wrong spot.
yeah, pi over 2, sine of pi over 2 is positive 1, not negative.
What, like the negative in the bottom left side?
Yeah.
On R.
Okay, so negative, the wrong place, negative.
Yeah, it's just
Okay,
wrong.
so I messed up in two ways. Okay, it then works out. It works out, right? Okay. Just gonna sign alpha over here. Okay. Okay, alpha is pi, then cosine of pi is -1, right? Right, and sine of pi is 0. Okay, so the matrix becomes -1, -1, 0, 0. Looks familiar? What is it? It's the same as the symmetry, same as the flip about the original. It turns out it's the same as the rotation through 180 degrees. Okay, so you can have a negative, you can have 2 pi, which will bring it all the way back. So that works out just fine as far as formulas are concerned. And as far then, let's see, we have almost everything taken care of on the plane. On the plane is almost everything is taken care of. But you can imagine that we cannot, this is a very important matrix, because even in high dimensions, it's still, you can still rotate. You can still rotate through any angle, but the only things that changes is you can pick different axes. So there's only one point to rotate around when the dimension is 2. If you have a three-dimensional space, you can literally pick any axis and rotate around it. Okay, or you can have consecutive rotations around the x-axis, y-axis, z-axis, and you have what you're going to get, hard to tell. Okay, so so we'll get to that, back to that again. There is actually an easy way to create a matrix in general. So this was working out fine for the standard basis, and now, well, it's still standard basis, but how do I find my matrix without going through solving equations or guessing? That's what we have been doing. We're guessing. It turns out it's very uncomplicated if you look at let's look at this example at the top. 0, 1. What is 0, 1? Where does 0, 1 come from? Zero, 1 is 1, 0 rotated. So if I start here with 1, 0 and rotate it 90 degrees, I will get 0, 1. Okay? So in other words, what is it? It is the image or the value of my function at the first basis vector. So 1, 0, where does it go? It goes to 0, 1. So bam, we have the whole column is right there. The whole column of my matrix is found. And the same thing with the second one. So what is this? It is 0, 1 rotated. So if I start with this and rotate it, I'll get that. Okay, so all I have to do then is to find the values of the two basis vectors, and I have my matrix ready. Okay, so we'll talk about that next time.